Hello, and welcome to the video on 6.2, the natural base, which is E. So we're going to start off this section by learning about the natural base, which is E. All right, it stands for Euler's number. All right, it's an irrational number, similar to pi, where it's going to go on forever. And they realize that as E approaches positive infinity, the number is 2.71828182846 ... goes on forever and ever. All right, so it's going to be an irrational number that can be used for quite a few things that we have. We want to make sure we know where the E button is on our calculator. So depending which one you have, you need to try to figure out where it is. On the 84 plus CE, the color one, if you press the second button and go down to where it says ln, kind of right next to the 4, it has e to an exponent. And if I just did that to the first power, that would once again give us Euler's number, or E. Okay. So as we go through the first couple examples here, it's just like a variable when we go through. We're going to use the same properties of exponents we normally would. If the bases are the same and we're multiplying, we add the exponents. So this would just be e to the 9th. Now if we wanted you to actually find that value, we could, but all we're talking about here is just using our rules of exponents to simplify the expressions. If we look at example 2, 16 over 4 is 4. E to the 5th over e to the 4th. Well, when we divide bases, we subtract the exponent. The 5 is greater than the 4, so it'll be 4e. Right. If you want to write the 1 as an exponent, you can. You just don't really have to. All right, same properties here. Remember when we do this and distribute this 2, it goes to each of our terms. So it'll really become 3 squared times e to the negative 4x times 2. So we'll end up with 9e to the negative 8x. All right, so that's just showing you that we can use some of the same properties of exponents to simplify things with the base of e. All right, if we go down and look at here, so we're now going to see some functions here that will be of the natural base. So just like in the previous section, when we talked about growth and decay, this will be similar. All right, as we go through it here, all right, we're going to have an equation that's going to tell us, well, this is going to be a function of the form y equals a times e to the rx. Okay, so it's a little bit different than the previous one. The a is still the same, except now instead of b, we have an e and we have an r in front. All right, so when a is greater than 0 and r is greater than 0, it's exponential growth. Okay. When our a is greater than 0 and our r is less than 0, it's exponential decay. All right, what does that really mean? If the e is being raised to a negative exponent, it's going to be exponential decay. If e is being raised to a positive exponent, it'll be exponential growth. All right. So just a couple of the base functions that you could see. Here's y equals e to the x and y equals e to the negative x. We have our growth function when it's positive. We have our decay function when it's negative. Okay. And we notice here if we plugged in 1, it gives us Euler's number at the top. All right. So now, for this next couple of examples, all right, we want to find the percent increase or decrease. All right. This is going to be very similar. We need to use our properties of exponents to be able to find the rate of increase or decrease. That's going to be close to of the form, like before, 1 plus r to the t, or 1 minus r to the t. That's what we did before when we used the properties of exponents. All right, we're going to do the same thing here. So to rewrite this, what we're going to do is we're going to do e to the negative 0.25 and then raise that whole thing to the t. So if we do that on our calculator, I would say second, that function, e, second ln, negative 0.25, and that's going to give me 0.7788 all to the t. All right, so when we think about that, this number in here is going to be less than 1, so we know it's going to be decrease. All right, and to get the rate, all right, think of the same thing. We would do 1 minus our r equals 0.7788. If we were to go through and get that, that would be 0.2212, which would be a 22.12% decrease. All right. How do I know it's decreased? Well, the original one had a negative exponent, so it's going to be decreased. That's one way to check, and we can also kind of tell here. All right. For the second one, I'm going to do the same thing. That 2 in front doesn't mean anything. It's totally separate. We're going to do e to the 0.4. Sorry, that should be 0.4. And then raise that whole thing to a t. All right, when we take e to the 0.4, it ends up become 1.4918, all to the t. This is more than 1, so it's growth, all right? And if I went through and did this, I would realize that my r would be 0.4918, so this would be a 49.18% increase, all right? And I could have written the r for the last one, I just forgot to write it there. Okay, once again, a couple ways we can check it. The number here is bigger than 1, so we know it's increase. All right, also we could tell that the exponent's positive, so it's also increase or growth function. All right, so just looking at 3 right away, we have that negative, so we know this is going to be decrease. All right, so I'm just going to write that right away because I know. And now I'm going to go through the same steps. E to the negative 0.55, raise that to a t. When I go through and do that, I would get 0.5769, right? Remember when we do this, we need to do 1 minus this number to get our rate. All right, so our rate would be 0.4231. So this would be a 42.31% decrease, okay? So remember, don't just take this number because it's less than 1 as the percent decrease. We need to do 1 minus that number to get our actual rate. Okay. Now, if you scroll down / flip over, depending if you print it or not. All right, we're going to get into kind of some more compound interest. All right. So if we remember from the previous section, we know that A equals the principal 1 plus the rate over the times compounded to the times compounded times the time. All right, is a formula for compounding interest when we're giving a specific number of times a year. Quarterly, monthly, daily, yearly, things like that, semi-annually, all right? So when interest is compounded continuously, this is important. So anytime you see the word continuously, we're going to use our function here, which is A equals the principal times e to the RT. Okay, this because the frequency of n approaches infinity, so they came up with this equation like in the front when we talked about Euler's number. All right, so the p is still the principal, just like in the previous one. The rate is the decimal, and t is the time. The only thing that goes away is the number times compounded because we replace that with e. All right, so anytime you see continuously, you're going to use this equation right here. Okay. All right, so a word problem here. It's just saying you and your friend each have accounts that earn annual interest compounded continuously. All right, the balance, A, in dollars of your friend account after T years can be modeled by, this should be A equals 4,500 times e to the 0.04t. All right, the graph shows the balance of your friend's account over time. All right, so we want to do your account versus your friend's account. So when we think about it, we're going to talk about which account has greater principal. If we look at ours, or so I'll say ours here, not yours. All right, we'll say we'll all share this one. So this is our account. So our account would have $4,500 as the principal. That's just our principal there. If we look at our friend's account, we would go through here and see that our friend has $4,000. So who has the greater principal? Our account has the greater principal. So we're starting off with more money in our account. We have $4,500. Our friend only has $4,000. All right, so now it says, which has a greater balance after 10 years? So now what we're gonna do is we're gonna say T equals 10, all right, and I'm gonna stick with red for our account. So we would say A equals 4,500 E 0.04 to the 10th, okay? So you can type that on as one thing. We could do 4,500 E to the 0.04 times 10, and we would get $6,713.21, okay? And this is for our account, all right? Now, if we looked at our friend's account, I'll continue to use purple. All we do, we don't have their equation, we would just look at their graph. So we can see the lines are going up by 2. So if I go to year 10 and just kind of follow it up here, it looks like it's going to be a little bit greater than $7,000, okay? So it's a little bit greater than $7,000. So who has a greater balance after 10 years? Your friend does, right? And we're just estimating that, and if we even did that, I would probably say it's approximately, I don't know, let's just say $7,250. Okay, that's a total estimation, but if we needed to, we can kind of tell there. Okay, all right. So another thing, there's someone else is going to say, well, you deposit $4,200 or $4,250 in an account that earns 5% interest compounded continuously. Compare the balance after 10 years. Okay, so for this here, once again, our principal will be $4,250. Our rate is 5%, which is really 0.05, and the T is 10. Once again, notice it says compounded continuously. That's important because we're going to use our account equals our principal times E to the 0.05 times 10. All right, and when we go through and do that, once again, 4,250 E 0.05 times 10, we would get $7,007, and if we rounded this up, 7 cents. Okay, so that's how much this other account would have after 10 years. All right, so just something to think about, right? Our original account had 4% interest. Our new one had 5%. Obviously, that should be a little bit more, all right, because it's a higher interest percentage, all right? And if we want to kind of think about this bigger picture, what could we say about our friend's interest rate? Well, our friend's interest rate is even greater than 5% because they have even more money than the $7,007.07. Okay, so it's not quite telling you that, but if we go through and look at some of the values we get, we can realize that our friend has the best interest rate out of all of these things. Okay, all right, our last example is going to compare interest compounded at a certain time compared to compounded continuously. All right, so if we look at it, it says you invest $4,000 in an account to save for college. Option 1 pays 5% annual interest, compounded semi-annually. What would the balance be in the account after 2 years? So our principal would be $4,000. Our rate would be 5%, which is 0.05. The N is semi-annually here, so that would be twice. And the T is 2 because it's also 2 years. So we're going to go back to use the one that we learned yesterday or the other day and now say, well, our account, our total value will be 4,000 times 1 plus 0.05 over 2 times 2 to the second, right? So 2 times 2, which is 4. All right. So as I go through this, I like to do the percentage divided by the times compounded. Add our 1, right? Caret, we're going to raise that to the 2 times 2, which is 4. All right, and then we're going to multiply it by the 4,000. All right, so after 2 years, our account, for this one account, will have $4,415.25. Okay, please make sure you think about this logically. If you end up getting like millions of dollars or like $50,000 or $500,000, obviously you want to check our work. You know, you're not making that much money, all right? Or, you know, some people will be a lot richer than they already are, okay? Option 2, says 5% annual interest, same interest rate. Now notice here, compounded continuously. So that's going to tell us that we don't need an N here. We're going to say our principal's $4,000, our rate's still 5%, and our time is still 2. So we're going to use, I refer to it as PERT, all right? So we take our principal times Euler's number, or E, the natural base. All right, and I like this one for many reasons, but we can just type it in. So 4,000 E to the 0.05 times 2, and we would get $4,420.68. All right, so it's only over 2 years, but you notice that just after 2 years with the same interest rate and the same money invested, we already have over $5 more in the account that's compounded continuously. So option 2 would be the better account to use. All right, that's it for today's video. Your homework will be posted. Have a great day. If you have any questions, let us know.